The first eclipse that we attended was in October of 1977. We were on a cruise ship off the coast of Mexico, and of course they had a lot of flexibility as to travel. There were a lot of clouds, and so they were able to move the ship around to find a clear spot. There was two ships out there, the Fair Sea and the Fair Wind. They had a lot of astronomers on board. I was able to meet and talk to Bart Bach and some of those really famous, I think Dr. Bach is gone now, but a lot of famous astronomers. It was really fun. They had learning programs. They had seminars going constantly, astronomy seminars. So that was the first one we saw, and that one was, I think, a little over 2 minutes. The next one was really an interesting case because it was February of 1979, and it touched part of the United States, I think Washington State or Oregon and Washington. Then it went across Canada. And so we were going with this Eclipse Chasers Club, which was organized by Dr. Harry Nelson at Augustana. And he had done this in Australia earlier, hired a plane and flew along the path of the eclipse because we were concerned about clouds. So he called United Airlines and he said, we'd like to hire a plane to fly us from Chicago up to Canada, not land, just come back to Chicago. So I had, my ticket says origin Chicago, destination Chicago. Kind of interesting, but we did. He talked to them and they said, well, what would you like us to do? Charter this plane? Yeah, okay. And I would like you to remove all of the seats from the right-hand side of the plane so that people can crowd around the windows to see the eclipse. So ride in all the seats on the left, on the right, to remove all the seats. And they said, I don't know, I don't think we can do that. And so Dr. Nelson called a good friend of his, Neil Armstrong. Neil Armstrong happened to be on the board of directors of United Airlines, so it was very quickly got back to Dr. Nelson and said, okay, we can do this for you. And so we did. We flew out of Chicago, seated in all the seats in the right hand or the left side of the plane, flew along the path of the eclipse, which would have been on the ground about 2 minutes and 40 seconds. And because we were moving along at like 500 miles an hour, we got 4 minutes and 40 seconds of total eclipse. So that was my second eclipse. My third eclipse was in 1991. We went to Hawaii, had a wonderful vacation out there, but we didn't get to see the eclipse because it totally clouded out. Although the people who went to Baja California in Mexico got a clear view of it, so I was kind of upset that I chose Hawaii instead of Mexico. We missed that one, and that was a long one. That was, I think, about a 7-minute eclipse.
Wow.
That's about as, I think the longest they can go is between 7 and 8 minutes.
I think so.
So then in 1998 we went on a cruise ship again in the Caribbean, went down to Aruba, got off on Aruba the day of the eclipse and set up, and we got these pictures here that I'm showing you. And so that was a great experience. We loved it, and so that was my 4 eclipses, 3 of which I've seen, and one I got to see cloud bottoms.
Good morning. Welcome to today's broadcast of the 2017 Great American Eclipse. My name is Jeff Struve, President of the Quad Cities Astronomical Society, located in the Iowa Quad Cities. This 3-hour event is brought to you by the Almighty and will be narrated by Dr. Robert Mitchell, Physics Department, St. Ambrose University, Davenport, Iowa. No planets will be injured during the making of this live broadcast. And now, Dr. Mitchell.
A total solar eclipse is that rare event when the moon completely covers the face of the sun, leaving only a bright corona surrounding what looks like a dark hole in the sky. The reason this occurs has to do with the moon's orbit around Earth combined with Earth's orbit around the sun. Seen from this vantage point in space, the moon orbits around the Earth counterclockwise. As the moon orbits around the Earth, we see different phases because we see different amounts of the moon's sunlit side pointing toward the Earth. During a full moon, the entire sunlit side of the moon is facing toward us, so we see what looks like a completely lit circle. New moon occurs when the moon is more or less between the Earth and the Sun, so that only the darkened side of the moon is pointed toward us. This is the phase when you have the potential for a solar eclipse. Now, if the moon's orbital plane was exactly lined up with the Earth's orbital plane around the Sun, then we would have a solar eclipse at every new moon. But in reality, the moon's orbit is tilted by about 5 degrees relative to the Earth's orbit around the Sun, so that most of the time, when we have a new moon, the moon appears to be either above or below where the sun is in the sky. And seen from the point of view of eclipses, that means that the moon's shadow misses the Earth, and so there is no eclipse. So the only way you can have a solar eclipse is when the new moon occurs at the same time that the moon happens to be crossing the Earth's orbit as it goes around the Earth. And even in those cases where it does, the moon has to be close enough to the Earth so that its shadow reaches the Earth's surface. You see, the moon's orbit around the Earth is not a perfect circle. There are times when it's farther away from the Earth than average, and times when it's closer to the Earth than average. So as a combination of all these factors, it's only about every 18 months on average that you get a total solar eclipse occurring somewhere on the Earth's surface. And that location is going to be different every time. Now, if you have the right conditions occurring, the moon's shadow comes in 2 parts, the umbra and the penumbra. If you happen to be at a location on Earth that falls under the moon's umbra, then the moon will completely cover the sun in the sky, and that is when you have a total solar eclipse. If you're under the moon's penumbra, then the moon is only going to partly cover the sun, and you get a partial eclipse. And as you can see in the diagram here, the moon's umbra gets narrower and narrower the farther you are from the moon, so that by the time it gets to the Earth's surface, at most, the moon's umbra is only going to be a little bit more than 250 kilometers wide, which is something like 150 miles. So it's only a narrow location on the Earth's surface that is actually going to see the total eclipse. Whereas the penumbra can be up to a few thousand miles wide, so many, many more people are going to see a partial eclipse than a total eclipse. And in fact, during those times when the moon is farther away from the Earth than average over the course of its orbit, the moon's umbra doesn't even reach the Earth's surface. When that happens, if you're standing under a location where the moon's umbra would have touched if it was close enough, then the moon does not completely cover the sun, even if it's dead center on it, but instead leaves a thin ring of sunlight around it. This is what we call an annular eclipse. And this is what an example of what an annular eclipse would look like in the sky. What you're seeing here is a map showing paths of totality. The path is each one of these curved yellowish lines showing the locations on the Earth's surface within which you would be able to see a total eclipse at some point or another during the moon's passage between the Earth and the sun. And this map shows you all the paths of totality for eclipses that have occurred across the United States of America from after the year 1776 up to the present day. And from this map, you can see that the last total eclipse that occurred anywhere within the continental United States was in 1979, almost 40 years ago. So it has been quite a while since the continental U.S. has experienced a total eclipse, although Hawaii managed to get one in 1991. What this map doesn't show you is that since 1979, the continental U.S. has had a few annular eclipses. And on this map, you can see the future of total eclipses for the North American continent. The current one, for August 21st, 2017, runs like just about across the center of the continental United States. and after that there will be some others. It's interesting to note that the track for the 2045 eclipse runs almost exactly parallel to that of the 2017 eclipse, just a couple hundred miles further south. On this map and on the previous one, you noted that totality tracks have different widths. For one thing, this is an indication of how close the moon is during the time of the total solar eclipse. When the moon is closer, its umbra is going to be a little bit wider on the Earth's surface, and therefore the totality track is going to be correspondingly wider. You can see the tracks for the 2024 eclipse and the 2045 eclipse are wider than the 2017 eclipse, which means that more people will be in the path of totality, and it also can give an indication of how long the duration of totality will be. For the 2017 eclipse, at most, the duration of totality will be about 2 minutes 41 seconds, whereas during the 2024 eclipse, you could conceivably have totality for longer than 4 minutes. And the 2045 eclipse is even wider still than the 2024, so you get even longer duration. On the other hand, it also depends on where on the Earth's surface the path of totality falls. Like the 2044 path of totality there in Canada is much wider than the 2017, but mainly because on that part of the Earth, the moon's umbra is getting spread out more because of the angle of the Earth's surface relative to it. So it's not necessarily going to be a longer duration, but it still nevertheless shows a wider area. Here's a more detailed map of the path of totality for today's total eclipse, showing some of the major cities that fall within it. Like, for example, Salem, Oregon, Douglas, Wyoming, Kansas City, and St. Louis, Missouri are on the edges of the path of totality. Clarksville, Charleston, South Carolina, and we are webcasting live from Aurora, Nebraska, which is approximately 20 miles due east of Grand Island. And here's a close-up map of Nebraska, showing even more detail as to what parts of Nebraska will be within the path of totality. To this webcast being broadcast live on YouTube, it is also being shown publicly in several locations around the Quad Cities area of Iowa and Illinois. The areas closest to the Quad Cities that will be experiencing totality are in central Missouri, and you can see a close-up map of specific locations in that state that will experience it. And southern Illinois will also experience it. Probably the most famous location in southern Illinois experiencing it is Carbondale, which, as it turns out, is also going to be in the path of the 2024 total eclipse. Although the Quad Cities area itself is not going to experience totality, there is a part of Iowa that will be experiencing totality. And here it is, about 450 acres of the extreme southwestern corner of Iowa, including a few back roads and no towns whatsoever. If you do happen to be in a location currently to be able to view the total solar eclipse, then by all means, we do encourage you to get out and watch it. This is truly a once-in-a-lifetime event for any particular location on the Earth's surface. But nevertheless, we must point out these important warnings. While the sun is totally eclipsed, it is safe to look at, with just the moon shadow completely covering it when just the corona surrounding it. But otherwise, we cannot stress this enough, never, ever, ever look at the sun with the unaided eye or through unfiltered binoculars or a telescope. As in never, 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 never. If there's any part of the sun showing through the eclipse, do not look at it unless you use the proper safety precautions. Now, I don't mean to try to scare you completely away from trying to view the eclipse. Just saying that you do need to use the proper safety techniques in order to view it. And there are a number of different safety techniques that you can do. Probably the safest method of viewing a partial to total eclipse is indirectly, like for example using the pinhole projection method. And it's really quite simple. All you do is poke a tiny hole in a stiff piece of cardboard or something, and use that pinhole to project an image of the sun onto a piece of white paper or cardboard or some kind of white screen. So then you're not looking directly at the sun, you're just looking at an image of it. Now, the farther the pinhole is from the screen, the larger the image will be. On the other hand, it'll also make the image dimmer, so you do have to strike some balance between how large you want the image to be and how clearly you want to be able to see it. It can help quite a bit if the white screen is inside some kind of deeply shadowed recess, like covered with a tarp or inside of a box or something, or better yet, inside of a darkened room if you can manage that. I've seen people make pinhole projectors out of very large cardboard boxes where they put the pinhole in one end of the box, put the screen inside on the far end of the box, and literally put their head inside the box so that they get a completely darkened view around it, just as long as they don't block the pinhole projector, and provided that the box is long enough that it produces a sufficiently large image. If you want to view the eclipse directly on, then you will need the proper filters in front of your eyes. One of the most inexpensive methods of doing that are eclipse glasses. There are some manufacturers that you can find online that produce these glasses. These are simple cardboard glasses. They're like the old 3D glasses that you used to see in movies, except the films on these are very specially made to filter out the sunlight so that it doesn't hurt your eyes. Now, you must make sure that eclipse glasses meet the proper international safety standards, where that they block all of the incoming UV radiation from the sun, all of the incoming infrared radiation, and 99.9999, however many nines it is, % of the visible light. So it not only brings the glare down to a much more comfortable level, but it completely shuts out the UV and infrared, which are those wavelengths that do the most damage to your eyes if viewed directly. If you want to view the eclipse through binoculars or a telescope in order to magnify it, then you need to fit your optical instrument with a solar filter, which again must meet the proper safety standards for filtering out the sunlight, and it must fit snugly over the front of the telescope. It works even better if it has fitting screws that will lock it securely in place. And you should also cover or remove the finder scope on your telescope for even more safety. If you don't have such a filter, there is still a way that you could use your telescope to view the eclipse. This would be by the projection method again. So what you do here is use the telescope as the projector and project the image again onto a white screen somewhere. Now this should only be done by astronomers who know what they're doing and keep the scope under constant supervision while they're doing this. Keep a close watch on your telescope at all times so it doesn't get too hot from the incoming sunlight. And don't let any passers-by try to look through the scope while you're doing this. For our webcast of the total eclipse, we are using the front-mounted solar filter method and installing the webcam in place of the eyepiece, so that is the image that you're seeing on the screen right now. Now, during the totality itself, we will need to remove the filter from the telescope. That is the only time that it is safe to view the sun with the unaided eye. So, as soon as the totality is just about over, you need to put your filters back on so that you don't accidentally get some of the unfiltered sun into your eyes. Now, if you're trying to take photos or videos of this with a webcam or a DSLR or whatever point-and-click camera you have, it may be okay to be unfiltered for a few seconds before and after totality, but you only want to risk your camera for this.
We'll be back in half an hour with more live coverage of the total solar eclipse from Aurora, Nebraska. In the meantime, we're going to leave you with a map of the path of totality, some mood music, and a view of the eclipse in progress.
Our star, the sun, is a big ball of gas, and it's 99% of our solar system's mass. It's an average star in our Milky Way, warming the Earth every day. makes it so bright. Come on and tell me what makes all that light. Hans Bethe long ago reached the conclusion it changes hydrogen to helium by nuclear fusion. When fusion takes place, light is created and it makes its way up,
although rather belated,
through the photosphere. That's the part that we see. The light comes out and shines on you and me.
about 1 million Earths could fit in the sun.
But if you were there, you wouldn't have much fun. It's 6,000 degrees at the photosphere,
And much hotter inside the solar atmosphere.
there are a few places where it's not so hot. Ooh.
Like at the center of a big sunspot. But heat is relative, it's still pretty warm.
Sitting on a sunspot would do you great harm. Galileo discovered sunspots. One of those things that's funny does. They're cooler parts, scientists feel, caused by a stronger magnetic field. The spots move around the face of the sun, proving to all solar rotation a strange kind of movement to do a full roll.
25 days in the middle, 36 at the pole.
What about flares? I've heard of them here. Like giant explosions in the chromosphere. The magnetic fields above the sunspots reconnecting again after being in knots. Above the chromosphere, the corona is placed. It's millions of degrees
And reaches way into space.
It's very thin, but read my lips. That's the part that you'll see in a solar eclipse. That's the end of our song about Mr. Sun. We hope that you find that lighting is fun, but never look at the sun. You could go blind. Just keep on enjoying that warm sunshine.
As the totality approaches, you're in a partial stage, and the crescent of the sun is getting narrower and narrower, and the excitement is mounting. And there's usually large groups of people around you, and you hear all this murmuring, and people just really getting very, very excited about it. And
Our star, the sun, is a big ball of gas, and it's 99% of our solar system's mass. It's an average star in our Milky Way, warming the Earth every day. What powers our sun and makes makes it so bright. Come on and tell me what makes all that light. Hans Bethe long ago reached the conclusion it changes hydrogen to helium by nuclear fusion. When fusion takes place, light is created and it makes its way up,
although rather belated,
through the photosphere. That's the part that we see. The light comes out and shines on you and me.
about a million Earths could fit in the sun.
But if you were there, you wouldn't have much fun. It's 6,000 degrees at the photosphere,
And much hotter inside the solar atmosphere.
there are a few places where it's not so hot. Ooh.
Like at the center of a big sunspot. But heat is relative, it's still pretty warm.
Sitting on a sunspot would do you great harm. Galileo discovered sunspots. One of those things that's funny does. They're cooler parts, scientists feel, caused by a stronger magnetic field. The spots move around the face of the sun, proving to all solar rotation a strange kind of movement to do a full roll.
25 days in the middle, 36 at the pole.
What about flares? I've heard of them here, like giant explosions in the chromosphere. The magnetic field above the sunspots, reconnecting again after being in knots. Above the chromosphere, the corona is placed. It's millions of degrees
And reaches way into space.
It's very thin, but read my lips. That's the part that you'll see in a solar eclipse.